Okay, before we go into the question, let's kind of go through some of the notes that might be helpful to us in solving the problem. So first of all, we have asymptotic rules. Like we know that asymptotically, big O is a upper bound, big theta is a tight bound, and big omega is a lower bound. Another mathematical definition for these asymptotic bounds is as follows. So suppose you have f of n and g of n that has some outputs larger or equal to 0. If you take the limit of f of n over g of n with n going to infinity, if you get an output of 0, this means that f of n is growing much slower than g of n. This means that f of n, the order of growth of f of n, can be asymptotically upper bounded by g of n, which translates to a big O bound. Okay, and as for the second case, like if you get some positive constant k, this means that the order of growth of f of n and g of f, they are kind of similar. So f of n can be theta bounded by g of n. If you get an infinity from the limit, this means that f of n grows like much faster than g of n. So, and in other words, g of n is kind of like an asymptotic lower bound for the order of growth of f of n. So this translates into a big omega bound. So here are some of the mathematical functions listed in an ascending order of growth. So we started out with like constants, and then some other orders of the functions that might be useful is that remember that logarithm, it grows faster than constant but slower than a linear function. And quadratic always comes before an exponentials functions. And as for the third node, we just hope to introduce this log star n function, which can be defined as the number of times that we need to take log of n until it returns 1. You will probably see log star when we are discussing about inverse Ackermann functions in the topic of amortized time analysis. Okay, so now let's go into the question. Like for 1a, we see that in g of n, the highest order term is actually the quadratic term. So we can kind of ignore the negative linear term. And when we compare the linear term of f of n and the quadratic term of g of n, we see that the linear term grows much slower than a quadratic term. This means that f of n can be big O bounded by g of n. For 1b, again, if you look at g of n, we see that since the highest order of growth term is the quadratic term, so we can kind of ignore the positive linear term. And when we compare the quadratic terms of both f of n and g of n, we see that they are basically similar. They share the similar order of growth. Like if you apply the mathematical limit definition to this case, you will see that if you take the limit of f of n over g of n, you will get a positive constant of 1. So in that case, we can actually safely apply a tight bound in this case, which is that f of n can be big theta bounded by g of n. Okay, for 1c, recall that we can ignore the constant multiplicative factor. So in this case, f of n will just be reduced to the linear term n. And in this case, we see that this is just the comparison that we have done before in 1a. So again, f of n can be big O upper bounded by g of n. Okay, in the case of 1D, we see that f of n takes a exponential term, whereas g of n takes a quadratic term. And recall earlier that in the ascending order of growth of the mathematical functions, we say that exponential term always grows faster than a quadratic term. So in this case, g of n is a asymptotic lower bound to the order of growth of f of n. So this translates into a big omega bound. Okay, for part E, if we look at g of n first, we see that we can kind of expand the power out to be 4 to the power of n, right? So when you compare these two exponential terms, we see that g of n definitely grows faster than f of n because its base is larger. So this translates into a big O bound. All right, for 1f, we see that there is a logarithm function and a linear function. Recall that a logarithm function grows slower than a linear term. Like you can again refer back to note 2 for that ascending order. So this will translate into a big O bound again. Like since the order of growth of a logarithmic functions is upper bounded by a linear function. Okay, for G, recall that we have already introduced the log star function, which grows very slowly. It grows slightly faster than a constant function, but it definitely grows slower than a linear function. So since it grows slower than a linear function, and a linear function kind of grows faster than a logarithmic function, we can see that the order should be log star, log n, and then n in terms of the order of growth in ascending order. So with that said, we can still be sure that the log star function grows slower than a logarithm function. So this translates into a big O bound. All right, that's all. Thank you.